You think a black hole is a cosmic drain you fall into. Then explain this. You cross the edge in minutes on your own watch, while your friend far away swears you never cross at all. Same astronaut, same black hole. Two true stories. So what is that edge? People say black hole, and the picture pops up instantly. A torn hole in the universe. Like space is a sheet, and something punched through it. And if you get too close, you fall through the rip into where? Somewhere else. A drain, a tunnel, a cosmic trapdoor. That picture is seductively simple. And it's the wrong mental model, because a black hole isn't a hole in space. It's not a place where space is missing. It's not a puncture you fall into. There isn't an inside of the universe and an outside of the universe separated by a rim. A black hole is a region where space-time is shaped so extremely that the future points inward. That sentence sounds like poetry. I mean it literally. Future, as in the direction your clock naturally ticks. The direction every cause pushes toward an effect. Near a black hole, the geometry tips that direction so far that going inward isn't a choice any more than tomorrow is a choice. But if that's true, why do we keep calling it a hole? Because something does look like a boundary, the event horizon. Cross it, and light can't get back out. Not because the light gets tired, not because there's a wall, because the geometry of space-time makes outward not a possible direction for any future-going path. Here's the problem. One black hole, one person falling, and physics gives you two stories that sound like they contradict each other. Story A, the falling astronaut. You're drifting toward the black hole. You feel weightless, like orbiting Earth. No engines, no air, no friction. You look at your wristwatch. Tick, tick, tick. Perfectly normal. You cross the event horizon, and if the black hole is big enough, you don't feel a bump. No shock. No special surface. No cosmic ding. Locally, nothing magical happens at that exact moment. You could even be holding a cup of coffee, and it wouldn't suddenly jump. So from your point of view, you cross the horizon in a finite time. A completely ordinary amount of wristwatch time. Minutes. Hours. Depends on how you start. Story B, the distant observer. Your friend stays far away, safely outside, watching with a telescope. They see you approach the horizon and never quite get there. You slow down. You fade. Your signals come in later and later. More red, more stretched out, like your time is melting, as if the black hole is making you freeze at the edge. So from their point of view, you never cross. Not it takes a long time. Never. Not in any finite time on their clock. Same astronaut, same black hole. Two true descriptions. One says you cross. One says you don't. And if you're a normal human being, your brain says pick one. Reality can't do both. But wait, physics is not in the business of picking the story that feels nicer. Physics is in the business of telling you what each observer can actually measure and what they can never measure no matter how clever they are. The contradiction is not in nature, it's in the pictures you're using. So the first job is to be painfully clear about what the event horizon is and what it is not. It is not a surface made of stuff. It is not a shell. It's not even a place you can point to in the usual sense, because it's defined using the entire future of the space-time. That's already suspicious, a thing you can locate only by talking about the future. Here's a more honest definition. The event horizon is the boundary of the region from which no signal can reach infinity. Infinity here just means far away, outside, where gravity becomes negligible. If you send a flashlight beam outward from outside the horizon, it can in principle escape and be seen by a distant observer. If you send that beam from inside, every possible future path stays trapped. Not because the beam is weak, because the set of allowed paths is different. You can even say it in a cruel way. Outside the horizon, you still have an out. Inside the horizon, the concept of out doesn't mean what you think it means. Now the whole picture encourages a second mistake, imagining the horizon as a kind of edge in space, like a circle you can draw on a map, like the rim of a well. But the horizon is not like the rim of a well. It's more like the edge of what can ever influence the outside universe. An influence is a space-time idea, not a space idea. It's about light cones, about which events can cause which other events. So why don't you feel anything crossing it? Because your body doesn't have a sensor for global causal boundaries. Your body can feel local forces, acceleration, tides, pressure differences. It can't feel the fact that somewhere far away, light rays from you will no longer be able to reach a certain region. That's not a local thing. An analogy, you're on a perfectly calm ocean with no landmarks. There's a border painted on the water that says International Dateline. Do you feel it when you cross? Of course not. But the rules for what day it is on the map change. That's not a force, that's a boundary and a description. Now that analogy breaks because the dateline is a human convention. The event horizon isn't. The horizon is carved into the causal structure of spacetime itself. Still, the point stands. Not every boundary is a wall you can stub your toe on. So where does the freezing come from for the distant observer? It comes from time, but not time as a feeling, time as a measurement. What distant observers call 1 second is not what observers deep in a gravitational field call 1 second. The clocks disagree, and they disagree in a very specific, measurable way. GPS satellites have to correct for it around Earth. Near a black hole, that effect becomes outrageous. Imagine you're falling and you send a radio beep every second according to your watch. Your friend far away receives those beeps. What happens? Each beep arrives more delayed than the last, and each beep is redshifted, its frequency lowered, because climbing out of gravity costs energy for the light. The light stretches. From far away it looks like your clock is running slow. Slower, slower, approaching a stop at the horizon. Here comes the catch. That doesn't mean your clock actually slows for you. Your clock, locally, does what clocks do. It ticks normally. It's the comparison between your clock and the faraway clock that becomes extreme. And there's another catch hiding under the rug. When the distant observer says you never cross, they're talking about a particular way of labeling time and space, their coordinates. A coordinate system is a bookkeeping choice. Some bookkeeping choices make a horizon look like a dramatic barrier at infinite coordinate time. Other bookkeeping choices don't. The horizon is real. The infinite time to cross is not a physical wall, it's a feature of that bookkeeping. But it still has teeth, because it matches what the distant observer can actually receive. If you cross the horizon, can you send them a final message that says, "I crossed"? No, you can't. Any signal emitted after you cross can never reach them. So from their practical point of view, they will never collect evidence of your crossing. They just receive an ever dimmer, ever redder echo of you approaching. So now the problem is sharper. Locally, crossing is uneventful and happens in finite proper time. From far away, you can watch the approach forever and never receive a crossing event. How can both be right without the universe cheating? That question is the doorway. It forces you to separate three ideas that your intuition keeps mixing together. 1. What you experience along your path, your proper time. 2. What someone else assigns as time to events near the horizon, their coordinate time. 3. What anyone can actually observe and verify using signals, causality, and redshift. And if you don't separate them, you're stuck with cartoons, a hole in space, a wall at the edge, a trapdoor to another dimension. So, hold on to the paradox. Don't resolve it too quickly. It's valuable, because black holes are the cleanest place where the universe tells you space and time are not the stage, they are part of the machinery. And when that machinery is warped enough, the words before, after, inside, outside, and even now stop behaving like they do in your head. That's the real topic. Not a hole. A geometry problem, dressed up as a monster. So let's earn the right to say geometry problem. Not as a slogan. As a working picture you can actually think with. Start with the one rule you're allowed to trust. In a small enough region, physics looks normal. That's the equivalence principle. You can always zoom in until space-time looks flat enough that you can pretend you're in empty space just for a moment, just locally. That's why a horizon doesn't have to feel special. Locally, you're just falling, and falling feels like nothing. Now zoom out. A black hole is not strong gravity in the sense of a big force you feel. What makes it dramatic is the way it reorganizes which directions count as future. Here's the cleanest mental tool for that, a light cone. Every event, every here and now, has a set of possible future directions. If you draw space sideways and time upward, the paths light can take make a cone. Inside that cone are all slower than light paths you could take. Outside are forbidden. You can't go there without exceeding light speed. In empty space, those cones all point straight up. Future is up. You can choose to go left or right a bit, move in space, but you have to move upward in time. In gravity, the cones tip, not because of wind, because of geometry. The upward direction is not aligned from place to place. Near a black hole, those light cones tip inward so severely that at the horizon the outward direction lies exactly on the cone. Light trying to go outward is in a sense barely holding its head above water. Inside, the cones tip past the point of no return. Every future directed path points inward, even light, and that is the event horizon in one image, the place where outward stops being a future direction. Notice what we did. We didn't talk about suction, or a drain, or a hole. We talked about which directions exist for cause and effect. Now, why does the outside observer get this freezing picture? Because they're labeling events using a time coordinate that behaves badly at the horizon. It's like using longitude at the North Pole. The geography is real, The coordinate system is the one having a nervous breakdown, but I don't want to hide behind coordinates. That can sound like a trick. So let's build an analogy that is not perfect, but is honest about what it's trying to capture. Imagine space as a moving river, not objects moving through space, a river of space itself flowing inward. Far away from the black hole, the river moves slowly. Closer in, it moves faster. At a certain radius, the river's inward flow speed equals the speed of light. That radius is the horizon. Inside, the river flows inward faster than light. Now, be careful. Nothing is literally flowing through anything. Space-time is not a fluid. This is just a way to picture the tipping of light cones. But it's a useful way because it makes two things intuitive at once. First, why you don't feel a wall. If you're floating with the river free-falling, you're not fighting it. Locally, the water feels calm, you're weightless. You cross the point where the flow reaches light speed, and you do not hit a barrier. The river doesn't have a fence at that point, it just has a speed profile. Second, why out stops working. Try to swim outward. Outside the horizon, if you can swim fast enough, you can make progress against the inward flow. Light is the fastest swimmer. At the horizon, even light can only just hold position. It tries to go out at sea, but the river drags in at sea. Net result, it hovers. Inside, even light swimming outward at sea loses ground because the river carries it inward faster than sea, so outward signals can't escape. That's not a force, that's kinematics in a warped geometry. Now bring back the outside observer. You, the infalling astronaut, are sending beeps. Each beep is like a little swimmer launched upstream. Near the horizon, those swimmers struggle. They take longer and longer to make it out, and they lose energy on the climb, so their frequency drops. That's the redshift. From the outside, the beeps get spaced farther apart. It looks like your clock is slowing, but you don't feel slow because you're not comparing your clock to theirs at a distance. You're just counting ticks on your own wrist. So where exactly is the paradox living? In the word time. There is not one universal time that everyone shares. There is your proper time, the time your body experiences. And there is the coordinate time used by some distant observer to label faraway events. Both are legitimate. They just answer different questions. Proper time answers, how much time passes along this path? Coordinate time answers, according to my chosen clock grid, when do I say that event happens? If you insist those must always agree, you're demanding the universe behave like Newton's universe. It doesn't. Now there's a sharper point that people miss. The outside observer doesn't merely see you slow down, they also see you dim and fade. And that fading is not just a camera problem, it's fundamental. Your emitted light is stretched to longer wavelengths. Each photon carries less energy as received far away. Also, the rate of arrival drops. Energy per photon goes down, and photons per second go down. The signal dies. So in practice, what happens is not that your friend watches you forever with perfect detail. They watch you for a while, and then you become unobservable. Not because you stopped existing, because the information gets infinitely diluted. That's the operational meaning of you never cross for them. There is no finite time at which they can receive a message proving you crossed. Your crossing event is outside their causal past forever, and now you can say something that sounds philosophical but is actually just physics. Different observers don't merely disagree about what happens at the same time. They can disagree about what events are even accessible to them at all. That's what horizons do. They carve space-time into regions of mutual ignorance. So are both stories correct? Yes, because crossing the horizon is not a single observer-independent moment that everyone can witness and agree on. It's an event on your world line that has a strange property. After it happens, you can't communicate it outward. You can cross, but you cannot broadcast your crossing. Now one more layer, because this is where the whole image really collapses. If a black hole were literally a hole in space, you'd imagine a missing region with an edge. But the horizon is not an edge of space. Space continues. You can assign coordinates inside, you can talk about distances there, you can do physics there. The horizon is not where space ends. It's where escape ends. So what is inside then? Inside is just the set of events that cannot send light to the outside. That's all. No trapdoor required. No separate dimension required. It's defined by communication, not by material walls. And the really brutal consequence is this. Once you're inside, reaching the singularity is not like walking toward a dangerous object in space. It's more like approaching a moment in your future. You can delay it a little by firing rockets, just like you can delay meeting tomorrow by sleeping in, but you cannot avoid it forever, because it lies in the same direction as your time. That's why calling it a hole is so misleading. A hole suggests a place you might avoid by going around. but you can't go around your future. Now, before you get too comfortable with the river picture, here's where it breaks. Rivers flow through a background. Space-time doesn't flow through anything. Also, the speed of space is not a universal measurable thing. It depends on the slicing of space-time you choose. The picture is a teaching tool, not a literal mechanism, but the light cone statement underneath it is not optional. That's the geometry. So the black hole isn't a hole. It's a region where the geometry rearranges causality so brutally that the outside and the inside become separated not by distance, but by the direction of time itself. And if that still feels like a word game, good, because the next step is to pin it to something you can almost compute in your head, what you would actually see as you fall, what you could actually send, and why the frozen at the horizon picture is both true and deeply misleading at the same time. Okay, let's make it visceral, not with horror movie language, with what you could actually measure. You're falling toward a big black hole. Big matters. If it's a stellar mass black hole, the tidal forces near the horizon can rip you apart. You'll feel them. You'll be stretched, spaghettified, before you ever get a chance to have philosophical thoughts about horizons. But if it's a supermassive black hole, millions of solar masses, the horizon is huge. The curvature at the horizon can be gentle. You can cross without being torn up right away. So picture the supermassive case. You're drifting in, weightless, no wall, no jolt. What do you see? You look outward, back at the universe you came from. Your friend's clock, the stars, their radio chatter. From your point of view, their signals are blue shifted. They come in faster. The outside universe seems to speed up. That's the complement to what they see. They see your beeps slow down and redden. You see their beeps speed up and blue. This is not just Doppler effect because you're moving. It's deeper. You're moving into a region where the relationship between your time and their time is skewed by gravity. Two clocks at different gravitational potentials don't agree on rates. And now a brutal question: do you see the entire future of the universe before you cross? People love that line. It's half true in the laziest way and false in the interesting ways. Yes, as you approach the horizon, signals from the outside can arrive in a compressed way relative to your proper time. The outside can appear to speed up. But no, you don't get an unlimited Netflix stream of the far future in a comfortable amount of wristwatch time, because the light that would carry very late events has to chase you down near the horizon and it gets distorted. In realistic situations, your view is limited by geometry, by the finite age of the universe, by the fact that black holes evaporate on absurd timescales, and by the fact that the light can become so blue-shifted that it turns into lethal radiation long before it carries you a nicely watchable story. And the deeper reason is this: horizons are defined by what can reach infinity, not by what you can see on the way in. Your experience is local. The global forever statements are about causal structure. So you fall, you cross, you don't notice the crossing itself. But you do notice something else if you're paying attention. After some point, the outside universe becomes irrelevant to your ability to affect your future. You can still look out. You can still receive light from behind you for a while. But you can no longer send anything that changes what they will ever observe. You are still you. You still have thoughts. But the outside world is now causally disconnected from your future actions. Not far away. Cut off. Now flip back to your friend far away with the telescope. They see you slow down and fade. So do they conclude you never fell in? They can't conclude you crossed, because they never receive proof of crossing. That's the whole point of the horizon. But they can conclude something else that is very physical. Your mass energy, your momentum, your charge. Whatever information can be encoded in long-range fields gets absorbed into the black hole's external influence. The black hole's gravitational field doesn't wait for them to see you cross. If you throw a rock toward a black hole, the gravitational field outside responds consistently with the rock's energy momentum being part of the system. In more precise language, the space-time geometry outside is determined by the total mass energy distribution. The bookkeeping about when the crossing happens depends on coordinates, but the external physics does not stop working. So there's a subtle but important correction to the naive "you never fall in" story. From the far observer's viewpoint, you never complete the crossing in their coordinate time, fine. But the black hole can still grow. The horizon can still be defined. The outside can still behave as if you were effectively absorbed, because the signals that would distinguish hovering infinitesimally above from just inside become impossible to retrieve. And that's the point. Never falls in is not a statement about what you are. It's a statement about what they can verify. This is where people get angry, because they want reality to be one crisp movie that everyone shares. But space-time doesn't hand you that. It hands you a network of possible signals. So what's the clean resolution to the paradox? It's not one story is wrong. It's that the event horizon makes what is happening now to the falling astronaut a question with no global observer-independent meaning. Outside observers can slice spacetime into nows that pile up near the horizon. Infalling observers slice spacetime into nows that pass right through. Both slicings are legitimate ways to label events. Neither gets to claim the other is fantasy, because the only arbiter is what can be measured locally and what can be communicated causally. If you want one sentence to keep you honest, keep this: the horizon is not a place in space, it's a property of spacetime's causal structure. And now the title becomes sharp. A black hole isn't a hole. A hole suggests missing space, a missing patch, a puncture you could circle around if you had a good map. A black hole is the opposite. It's not missing space-time. It's too much geometry. It's space-time doing something so extreme that the usual separation between where and when breaks down. Inside toward the center is not like walking north, it's like walking toward next Tuesday. You can thrash around, you can accelerate, but you can't choose a path that avoids the singularity any more than you can choose a path that avoids the future, because the geometry has made that direction time-like. That's why the horizon doesn't have to feel special. It's not a material boundary. It's the moment your future stops, including escape. And if you want the existential sting of it, without the melodrama, here it is. Your life already contains horizons. There are regions of the future you can still influence and regions you can't. There are messages you can still send that matter and messages you can't. We just don't draw those boundaries on a star map because they're not made of gravity. They're made of time, decisions, and irreversibility. A black hole is the universe drawing that idea with a ruler, perfectly, cruelly, mathematically. So the next time someone says a black hole is a hole in the cosmos, you can say no, it's a one-way boundary in the geometry of space-time. The weirdness isn't where you go. The weirdness is that two observers can tell two consistent stories because now is not a universal commodity. If you want to keep going with this, what happens to information, why Hawking radiation makes the story even stranger, and why the word inside becomes a dangerous word in quantum gravity, then stay with the channel. This is the kind of physics that doesn't ask you to memorize formulas, but asks you to rebuild your intuition until it stops lying to you.